Let's dive into one of the most mind-bending experiments in the history of physics. It all starts with something that sounds incredibly simple. You just shine a light on a piece of metal. But what happens next? Well, it was so bizarre, so completely unexpected, that it forced us to rethink everything we thought we knew about the very nature of light itself. So here's the basic setup for what we call the photoelectric effect. You've got a beam of light, and you point it at a special photosensitive metal plate. When that light hits the surface, something amazing happens. Electrons are literally knocked loose, right out of the metal. And as you can see here, if we set up a way to catch those electrons, they create an electrical current that we can actually measure. Seems simple enough, right? Well, that's where things start to get really interesting.
All right, to really get to the bottom of this mystery, we first need to understand the tools of the trade. Let's take a closer look at the really clever experimental setup that scientists use to poke and prod at this strange effect.
Now, this is what's so great about this experiment. We can control just about everything. Over here, we've got our light source. We can change its brightness, that's its intensity, and we can also change its color, which is its frequency. The light beams through a quartz window, and using quartz is key because it lets all kinds of light in, even ultraviolet, and it hits plate C, which we call the emitter. This is where the magic happens. Electrons get knocked off, they travel across to plate A, the collector, and boom, we get a current. But here's the really crucial part. We can apply a voltage between these plates, and we can even flip it backwards, and that, as you'll see, is going to be our secret weapon.
Okay, with our experiment all set up, it's time to start gathering some clues. And what the scientists found wasn't just a bunch of numbers. No, it was more like a trail of breadcrumbs, a series of really strange findings that pointed to a conclusion that nobody was prepared for.
So the very first clue seemed totally normal, completely straightforward. As this graph shows, the more intense you make the light, the brighter it is, the more photoelectric current you get. This makes perfect sense, right? A brighter light should have more oomph to knock out more electrons every second. So far, so good. Nothing weird here, yet.
Now remember that voltage we can control? This is where we get clever. What if we reverse the voltage so that the collector plate becomes negative? Well, then it's going to start pushing away or repelling the electrons that are flying towards it. If we dial up that negative voltage just right, we can find the exact point where we stop even the fastest, most energetic electrons from making it across. We call this special voltage the stopping potential, and it's so important because it gives us a perfect way to measure the maximum energy of those electrons.
And this brings us to this beautiful, simple little formula. It says the maximum kinetic energy of an electron, which we call Kmax, is simply its charge, little e, times that stopping potential we just measured, V0. This equation is amazing. It's a direct link between something we can easily measure in the lab, a voltage, and something fundamental about the electrons themselves, their maximum energy.
So let's put some real numbers on that to make it super clear. Let's say we do the experiment and we find that the stopping potential is exactly 2 volts. Well, that means the speediest electrons coming off that plate have a kinetic energy of exactly 2 electron volts. An electron volt is just a really convenient unit of energy we use when we're talking about tiny particles. So the takeaway is simple. The higher the stopping voltage, the more energy those electrons have.
Okay, get ready, because here comes the first really weird clue. Take a look at this graph. Those lines I1, I2, and I3 show 3 different light intensities, where I3 is the brightest. Just like we saw before, the brighter lights make a bigger current. But look over to the left. All 3 lines hit the same exact stopping potential. This is huge. It means making the light brighter kicks out more electrons, but the fastest ones all have the exact same energy. That just doesn't feel right. It's like saying a giant tsunami wave hits the beach with the same force as a tiny little ripple.
And the plot just keeps on thickening. What if we keep the brightness the same, but instead change the light's color, which is its frequency? Well, look at this. The frequency V2 is higher than V1. Think of it like blue light versus red light. And you can clearly see that the stopping potential for the blue light is way more negative. What does that mean? It means the higher frequency light is kicking out electrons with more energy. So it's not the brightness of the light that gives electrons their energy, it's the color. And here it is, the final, most baffling clue of all. It turns out that for any given metal, there is a specific cutoff frequency, something we call the threshold frequency. If you look at the graph from metal A and metal B, you can see this no-emission region. If you use light with a frequency that's below that line, absolutely nothing happens. Not one single electron comes out. And it doesn't matter how bright you make the light. You could blast it with a light as intense as the sun, but if the frequency is too low, you get nothing. So, we have our clues. Now, for over a century, physics was built on the idea that light was a wave. It's time to put that classical wave theory on trial and see how it holds up against this strange new evidence.
The main idea behind the wave theory is pretty intuitive. It pictures light's energy as being spread out all over the place, kind of like how the energy of an ocean wave is spread across its entire front. In this view, the brightness or intensity of the light is all about the wave's amplitude, basically how tall the wave is. A bigger wave should mean more energy.
So first charge against the theory, intensity. The wave theory would predict that a more intense light wave, a bigger wave, should smack the electrons harder, giving them more energy and making them fly out faster. But what did our experiment show? Reality was crystal clear. Intensity has zero effect on the electron's maximum energy. The theory and the facts are in total disagreement.
Second charge, frequency. According to the wave idea, an electron on the surface could just sit there and soak up energy from the light wave over time. So it shouldn't matter what color the light is. As long as it's bright enough and you wait long enough, the electron should eventually absorb enough energy to pop out. But what's the reality? A hard cutoff. Below that threshold frequency, nothing ever happens. The wave theory has no way to explain this at all.
And the final fatal blow, time. If light energy is really spread out like a wave, people calculated that it should take a really long time. We're talking minutes, maybe even hours, for one tiny little electron to absorb enough energy to escape. But what did we see in the lab? The electrons came out practically instantly, in less than a billionth of a second. It wasn't the slow soaking up of energy. It was more like an immediate collision.
The case is closed. The evidence against the classical wave theory is just overwhelming. On every single major point, it completely fails to explain what's really happening. The conclusion is pretty clear.
So, the verdict is in. The wave picture of light, a theory that had been a pillar of physics for 100 years, just completely falls apart when it comes up against the photoelectric effect. It can't explain why energy doesn't depend on brightness, it can't explain the threshold frequency, and it can't explain why it all happens in an instant. Physics desperately needed a new idea. So let's just recap the undeniable facts that this experiment gave us. Brighter light means more electrons. Simple. The stopping potential is our key to measuring the maximum energy of those electrons. And crucially, it's the light's frequency, its color, that determines that energy, not its brightness. And finally, there's always a minimum frequency you need to even get started. These are the laws of the photoelectric effect, and any new theory would have to explain every single one.
And this all leads us to one final, massive question. For a century, light acted exactly like a wave. But here, in this experiment, it refuses to play by those rules. The old theory is broken beyond repair. So, if light isn't a continuous wave washing over our surface, then what in the world is it? The answer to that question was about to change everything.